Let us now detail the set of parameters we need to specify when implementing a convolutional layer. There are 4 different parameters for convolutional layers: the kernel size, the depth of the output volume, the stride, and the zero padding. The size of the kernel is typically of 3 by 3 or 5 by 5. Usually, we just mention the spatial dimensions of the kernel since, as we have said before, the depth of the kernel is usually set to the depth of the input volume. Therefore, the depth of the kernel needs not to be specified. In this example, the spatial size of the kernel is 3 by 3. The depth of the output volume, or equivalently the number of feature maps, needs also to be specified. In this example, we set it to 6. There are 6 feature maps created from 6 different kernels. Increasing the number of feature maps results in an increasing number of tuning parameters in the kernels, but also corresponds to extracting more complex representation from the data. The 6 feature maps are represented as one volume called the output volume, and you see that its depth equals the number of feature maps. The stride corresponds to the shift of the area of interest, the receptive field, the pink area in the previous pictures, when computing the convolution. There is only one parameter, the stride, for the horizontal and vertical shifts. Usually, the stride is set to 1, more rarely to 2. On the left, you see an example of a stride equal to 1, and on the right, a stride equal to 2. The size of the zero padding is the number of zeros you add to the border of the image. On this example, you have an image of size 4 by 4, which is surrounded by 2 strata of zeros. In this case, we have set the size of the zero padding to 2. This is particularly useful to reshape an image or ensuring that the output image has the same shape as the input image. A kernel is then applied to the whole image, here an image of size 8 by 8, which results in a bigger output feature maps than the one obtained without applying zero padding. There exists a relation between all the previous parameters and the dimension of the input-output. Can you find this relation? This relation is useful when one wants to have outputs of the same size as the input. You can then choose the last parameter to satisfy the relation below with O equals to I. I encourage you to try to derive this relation, which is not too complicated to obtain. So we have seen what is convolution, but why do we want to use it? Convolution consists in applying the same transformation to all parts of the image, which takes into account the spatial dependence between pixels. Convolution is also able to detect a pattern wherever it is on the image and has thus shift invariance properties. Taking into account spatial dependencies between pixels and being robust to shifts are 2 major differences between CNN and classical neural networks. Since the input image contains millions of pixel values, detecting small meaningful features, such as edges, can be done with kernels that use only a few hundred of pixels. This is the difference with classical neural networks that use dense connections, fully connected layers, contrary to CNNs that use weight sharing and sparse connections. Indeed, here is a representation of the difference between dense layer on the left and a convolutional layer on the right. You see that on the left, all neurons of one layer are connected to all neurons of the next layer, with different weights for each connection. On the right, the convolutional layer is sparse. Not all neurons of the first layer are connected to all neurons of the next layer. Besides, some weights are shared between the existing connections. The fact that convolutional layers contain less connections and the fact that they share weights imply that they contain less parameters than classical neural networks. Convolutional layers are then easier to optimize from a statistical and computational point of view. Weight sharing, which imposes equality constraints between some weights, can be seen as a form of regularization, which partially explains why it helps preventing overfitting. Note that even if it is possible to write convolutional layers as a scheme on the right, we will always use the representation we have seen so far with images, which is easier to understand.